Good evening, sir.
Uh, Good evening, Srinivasan. Thank you very much. Again, I'm disturbing
Not
you.
at all.
Thanks.
Sir, please, sir, not at all. Hope you are able to connect from the tab also, sir. Both
Yeah,
tab
yeah,
and
tabல
laptop.
இருந்து தான் கனெக்ட் பண்றேன். இன்னைக்கு வந்து no MATLAB. I have to 1 or 2 days. I have to go back to theory. Then I have to
Yes,
go
sir.
back
Yes, sir. Continuation
vigorously
of
to MATLAB.
yes, sir.
Yeah,
Yes, sir. Yes, sir.
I'm just waiting.
Yes,
Good
sir.
evening, Arjun, Josan.
Good evening,
Good
sir.
evening, sir. Good evening, sir.
We'll wait for a few minutes. We'll quickly run through what we did so far, and I have one more topic to cover before we take a lot of applications. Uh, One of the best things to do, see the actually the applications directly in medicine is slightly difficult. Okay, but there are simple applications. Medicine means in the sense that physiology, which I'm going to, in fact, I'm going to offer a course on quantitative physiology next semester. Right now, it's slightly difficult. We'll see some examples from quantitative physiology also. But there are a lot of simple examples in pharmacology, in drug, how it interacts, how equations are written for drug interactions, all those kind of things. So how it's absorbed, how it's excreted, all those things we can write down with a with equations. Okay, so that with that as a base, it is easier to deal with many examples, but it'll take some time because we have to go back to some theory before we uh, go to many more examples. Okay, at that time we will go back to MATLAB. Itself, next class itself, we'll go back to MATLAB. But till then, some conceptual understanding is required. So that is what I'm going to do uh, in the next, in today's class. Uh, okay, I'm going to quickly run through. Any of you have a problem with anything which I have done? Stop me at that time. Okay, and I will explain that part. Okay.
Okay, sir.
Yeah, I have to 1 second. You're able to see my screen?
Yes, sir.
Yeah. So what did we do? It all started with what are called functions. It all started with what are called functions. The another name is mapping. So the functions, what we said, operates on a variable and it gives you another variable. This is the simplest function. We are going to see as we go on more complex functions, but right now I can say that this is the simplest function. So here we say that x is an independent variable and y is a dependent variable because I operate independently on x and I get y. What I get y is dependent on x. So, for example, y is equal to 2x is a function. If I give a value of x is equal to 2, I get value of y is equal to 4. So y depends on x. So it's called dependent variable. It can be very complex, simple like this, slightly more complex. It become more and more and more complex. Okay. Now that's the first thing. So we are going to deal with all things which ultimately uh, boils down to in any sphere, forget about medicine, or functions. The functions are also called equations. Okay, it's just a synonym. For example, this is called as a quadratic equation. What you see here, okay, and so on. So functions and equations are they are interchangeably used. There is always a region or an interval in which this can work. For example, this function may be valid in an interval between 3 and 5. If I put a square bracket like this, then 3 is included. If I put a bracket like this, 3 is not included, but something which is very, 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 very close to 3 point not, I can write 100 knots 1 just before. So 3 and 5 are not included. If this is the bracket, a square bracket means both of them are included. So in other words, this is what it means. So this 3 and 5 is called a domain, and that is taken to what is called as a range. So just if you look at this function 2x, that's the function. It takes all the points between 3 and 5 and takes it to another area which is between 6 and 10. So this is the domain of operation of this function, and that is the range that it goes. The functions can be anything. It can be 1 by x. It can be anything, can be an independent variable. T is, for example, an independent variable. Okay, and so on. So that's the first thing. Now, sometimes there are functions which behave in a different fashion. Here, this function is 1 to 1. Give x, I know y. There can be 1 to many. Like if I have square root of 4, or rather, I would say y is equal to a square root of, say, x, then x can be plus 2 or minus 2 if, y can be plus 2 or minus 2 if x is equal to 4. So that 4, this is the x region, which we called as domain, takes you to y region, and it can be plus or minus. So it's 1 to many. Okay. Now, this is many to 1, just opposite to it. So if I say y is equal to x squared, then if x is equal to plus 2 or minus 2, y is equal to 4. So either way, I take it to 4. So this is called as many to 1. Now, what is the difference? Okay, the question now I'm going to ask you is, what is the difference between this, and this? So let me draw that here. What is the difference between this, and this, and this? So, what is the difference between these three? Now, the difference is with respect to inverse function. Can someone comment?
The inverse function would be invalid for the first two.
Exactly. Fantastic. Because I want one value here to go to one value here. Because if I now choose 4, I don't know whether I have to go to plus 2 or minus 2. Okay. So I can't write this as a function unless, like, you and I understand it and write it as plus or minus 2 and say that it will go to plus 2 or minus 2. But it becomes difficult. So we will deal only with these kind of functions. Okay. If it requires an inverse.
Sorry, but the first one also, if there are more than one value to y, is it valid as a function? You were saying like it should have only one.
So here this x goes to, so this side function. Okay, I'm going to write it as, so that's what I said. I understand that it is plus 2 or minus 2. So 1 to many. Okay, it is a function. We are only talking about inverse. I'm only talking about from, so here to here, while going, I can define it. But from here to here, when I go, unless I put some special things, okay, special conditions, it's not valid. So it is not 1-to-1 means it's a neat inverse function. Is that clear? So when I say 4 goes to plus or minus 2, that is x is equal to plus or minus 2, okay, it is what? It is still a function. I'll call it as one-to-many function. When one-to-many, like that, this is many-to-one function. But when I get an inverse and you ask me, I'm giving 4, okay, from where did it come? If you ask me that question, okay, I wouldn't know whether it came from plus 2 or minus 2. It would have come from plus 2 or minus 2. Is that clear? So I won't be able to answer that question. I won't be able to express it. I won't be able to give a unique. So this is unique. I won't be able to give a unique answer. That's the problem. Is that clear?
Yes.
So it is the uniqueness that matters. Now, as I said, I can keep on increasing the order there, 3. When I go to, this is cubic. What you have seen here is cubic. Then I can go to x power 4, quartic, and so on. Okay, I can just keep going on. And so ultimately I can write n. Like for example, this is a function, y is equal to a1 x power n plus a2 x power n minus 1, blah, 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 up to a0. This is called as a polynomial function. Very popular. We are going to see this quite often. It's called polynomial function. Monomial, 1, polynomial. That means that a number of powers are involved. Poly, number of powers are involved. So usually, in mathematics becomes difficult for many people because of one fact, that if I write like this, write like in this fashion, people, it's easy to understand. But the mathematicians don't want to, they're lazy guys. They don't want to write big equation. So they will write a small equation like this. So they compress the whole thing and put one sigma here. So that sigma simply means expand. That's all. Okay. So there are 2 symbols used. Here I've used a sigma symbol, which means that sigma ai x power I, which means that a1. So I also write the range 1 to n. a1 x power 1 plus a2 x power 2 plus all the way up to an x power n. So this whole thing, I am reducing it to writing it as a sigma. Is that so? Many people get confused with the sigma. Sometimes what they do is they'll put like this. Okay. So when they put like this, say xi, I is equal to 1 to n. This is a multiplication, which means that x1 into x2 into up to xn. So multiplication. Multiplication is by that big capital A. Okay. So another symbol. Now x, I am going to take from real numbers. Real number is written like this. That's a real number. Now, when I say that I'm going to take this, for example, 3 to 5, I took it from real numbers. That means there are also imaginary numbers. Let's not worry about it right now. So we took this from real numbers. And so I write it like this. So I say X, which is a member. This means it's a member of the community called real. Okay. Now, so I am taking X and from a real number and getting you Y. Now, there can be functions which can have 2 values. What do I mean? So for example, I can have y is equal to a1 x1 plus a2 x2 plus say a3 x1 x2. So which means that there are 2 values of x1 x2 Okay, the two values. Now, then I will write y now is a function of x1 and x2. Say, if you are worried about this a1, I can write y is equal to 3x1 plus 4x2 plus 5x1 x2. That's multiplying. So this now is a function of x1, x2. There are two values. So what we do is then we write f. Okay. Now f with one underscore. Look at that carefully. Look, underscore this, which means that it is not just one value. There can be more than one value on the right hand side. This is the simple way of writing. So which means that x, which I have written, how many values you will, next question you will ask me. Then I'll say x is a member of R2. That means this 2, will tell that there are two values. Suppose y is equal to a function of x1, x2, x3, x4. Then I would say x is now a member of R4. You will know automatically that the real number has 4 values. Clear? So these are all notations which you will see in many, many, many books. Okay. So still we have not lost the idea of functions. Usually functions can be continuous or discontinuous, or can be defined, or in other words, can be defined in a range or in domain, different domains. So for example, if I have a function like this, y is equal to 2x plus 1, x less than 1, it takes this value. X greater than equal to 1, it takes this value. So there is one jump there. Okay, possible. But here actually it's not so, because it is 1, 2x1, x is equal to 1. See, look at this. How does this become? So 2x plus 1. So from 1 it starts, goes up. Okay, and at this point, okay, when x is equal to 1, what is this value? 2 into 1 plus 1, that is 3. According to this equation is also it is 3. So this will have a different slope. So there are two lines like that. This operates, okay, after 1, and this operates before 1. So there are two linear curves. So this is called bilinear curve. Two linear curves. Okay. So we will see what is continuity in a minute, and so on. So there are complex numbers. I'm not going to go into that now. Root of this, we had a discussion, when root of -2 means it's a complex number. There can be more than one function, f and g. Okay. So you can add this. So get f plus gx is f of x plus g of x. F minus g means f of x minus g of x. I'll send you this whole notes to you, but just listen now. Okay. I'll stop for a minute. Is that okay? Understood? Dr. Shanti, any questions?
No, it's clear. Thank you.
Yeah. Okay. Oh, for all there, I'm not able to see. 1 second. Yeah, Dr. Sundar, is that clear?
Yeah, yes, sir. I am following.
Yeah. Dr. Bhagyam?
I'm following.
Yeah, great. Just how do you get it back? Yeah. 1 minute. Yeah. Okay. Now I can multiply it. I can divide it. And I have a very important tool or a role. So it can so happen that I can write y as a function of x. Then I can write z as a, now that, I mean, I have to use a different symbol now, as a function of y. Okay, now I think I wrote the other way in this, sorry. G, okay, and f. So what does this mean? That means that I have x, okay, from x I go to y, okay, using this equation, okay, from y I go to z using this equation. So this f takes me to z, g takes me from x to y, okay. So I write this jump two things, a complex or a contracted function f of g of x. So this gives me y, and then that gives me f. So that's also possible, this kind of functions. Okay, so we had seen examples for it, and it's very important to notice that it's one way. I can't do the other way. They are two different results. Okay. Now we had seen an example how the optical density about the bacterial population size and so on. I will not go into all the examples. Then we also noticed, okay, that there are various ways in which this function behaves when we start plotting. It can have a minimum value, globally only minimum value, or it can be an oscillating function which goes up and down, okay, or it can be monotonically increasing like this. So this we had already seen, but if this is not the case, I can have an inverse function. The inverse function, when the function f takes x to y, the inverse function acting on y takes to x. So when I operate together f inverse x, f, then I will get y. So it's something like f into f inverse is what is called as an identity. Identity means a function which operates on y gives me y itself. So this is identity. Okay. We had seen some example. Rational function means there is a numerator and a denominator. Okay. Then sin x, cos x, tan x, and all are called as transcendental functions. Okay. So, for example, the addition part we saw, and that's the transcendental function. Okay. And so on. Right. Many functions behave in biology and medicine as Michaelis-Menten equation is an example, behaves when it reaches a saturation limit. This is saturation limit. So actually it doesn't, for example, an equation of the form AC divided by Km plus C. Okay. The concentration keeps increasing. The concentration here in this equation, concentration keeps increasing when C is much bigger than Km. So this equation now, if Km is 1 and I'm going to C is equal to 10, 100, and so on, then this equation AC by Km plus C is approximately equal to AC by C, approximately. Okay, and so this and this cancels, and the function becomes A, but it will never reach A. So then in that case, we call that it asymptotic asymptotically reaching A. It's a horizontal asymptote. Okay, it's a horizontal asymptote. So asymptotically reaching A. So power functions is what we saw. We plotted it. They behave, depending upon the value of R, they behave differently. Okay, they behave differently. So if you now look at point 3, for example, okay, the curve would look like this. If I now look at 3.5 x power R, I'm talking about y is equal to x power R, then it will behave like this, and so on. But at 1, they will all cross, because 1 power, whatever it is only 1. But depending upon that R function, the curves would look, something will be increasing forever, depending upon whether it's less than 1 or greater than 1, and so on. Okay, so similarly, we have seen all these functions. There are different types of functions which will behave, okay, depending upon the values they carry, they will behave differently, which we have seen. I want you to plot all those functions. Okay, we saw an example, and then we saw that there is an oscillating function. Okay, we fill this up, the amplitude, the phase, and the period. Okay, we're going to see more about this later, but just want to revise that. So we saw that sine, if it's a function which takes from minus pi by 2 to plus pi by 2, okay, takes from -1 to +1, arc sine, sometimes written as sine inverse of x, okay, takes you from this value to this value. Okay, but we're going to find that that's not a very nice function, actually. That's not a one-to-one, that's what we are going to see. But we write this nevertheless to minus x, sine inverse of x, and then see, when this operates only between this range, it's a nice function, there's no problem. Okay, then it becomes an one-to-one function. So the domain defines the behavior of the function. Okay, so there's further examples on that. So e power x is a very powerful example. Okay, very powerful example. Whether e is equal to x is equal to plus or minus, the way it behaves will be very different. E power x will just keep, when x is equal to positive, it just keep increasing. E power minus x, when x is negative, it will keep decreasing. Okay, then we defined a log as one which is inverse to this e power x. E power x is another important function. That's going to be there in many situations. We are going to face it. So e power x takes you from one domain to one range. The inverse function for e power x is a log function. Ln means we say that there's a base to it. The base is called e. So how does this behave? So we say x is equal to log to the base e of y. Okay, so you can see that, in which case y is defined as e power x. So in other words, if y is equal to e power x, log of y to the base e takes me to x. So x took me to y by e power x. Log of y, what is called base e, takes me back to x. So this is an inverse function. That base e becomes important because this is what e power x. Suppose I can have any base. People use log to the base 10, okay, of y. Then what does that mean? 10 power x is equal to y. So if there is anything apart from E. Say, for example, if you have 2 power x function, one function, that is 2 power x. So what is the inverse of that function? So then x is equal to log to the base 2, okay, of y, because 2 power x, log to the base 2. So base, as I call it, depends upon to which this fellow is raised. Clear? Any questions? Any questions? No questions? Clear?
Yes, sir.
Yeah. Now, log xy. Okay, log means ln means log to the base c is x plus y. I don't want to prove this, but just take that. It's x plus y. So log to the x power p. Look at that. X power p is p log x. Log of 1 by x is minus log x. So these are, so log of x by y is log x minus log y. You have to be very careful. Very careful. Say log of x plus y is not equal to log x plus log y. Can anyone tell me why this is so? Just out of curiosity. So look, this is to the base e. So let me say z is equal to log to the base e xy. Okay. So you can see that I can't write e power z. Okay. So I have to now write it down into 2 parts. So which means that log x plus log of y to the base e is equal to z. Okay, I can't write it like what I did before, right? But though I can say that x, y, that is, it can come in here, and I can write e power z is equal to xy, but this is the actual function which represents this kind of thing. Okay, so that is why we write log xy is log of x plus log of y. Okay, we saw some examples for this. So we also talked about, we'll see more about how sine and cos works, okay, and about sine theta. They're simple things. Then we also said that there are continuous functions, and there are what are called as discrete time functions. Discrete time functions is that, see here, it's a continuous function. F of t, y is equal to f of t. So which means that t can take any value. It's a continuous function. 1.1, 1.11, 1.100001, whatever it is. Okay. Now, the other thing that is important to us is a discrete time function, which means that it is at a particular time. And say, for example, function is defined only at 4, 5, 6, and so on. As I told you before, suppose you want to take temperature of a patient at morning 9 and evening 6. Okay. So you can say that what is available, the temperature that's available is, okay, a function of a discrete value. Say at 9 a.m. first day, then or 6 p.m. second day. So these are all discrete. Actually, you don't know what happened between 9 and 6. Maybe it had increased at 2 o'clock and then come down at 6. You don't know. So you have only values in discrete points here, 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 and so on. So that's why it's called discrete time functions. Right? So we write, say, for example, the first, first day, the patient takes data, it is T1, the first day at 9. Then evening he takes data, I'll write it as T2. Next day he takes data, it's written as T3. Next day evening is T4, T5, and so on. So these are discrete values. Many times I can have a relationship between these values. Okay, these values. So that's the next thing we saw, that I can have a relationship, something like this. 0.5 mt plus 1. So t plus 1, mt plus 1. So m, say, I wrote it for t, I wrote it for m, whatever be the value. I just replace t by means of m, and I can write it as m1, m2, m3, okay, up to whatever it is. So m t plus 1 is equal to 0.5 mt plus 1 is an equation which we wrote for looking at how, for a medicine, when it's given, how that functions. Right. So now I just substitute the value of t. So first instant plus 1 is equal to second m2. So m2, if I say this temperature is this equation, then m1 will give you temperature during the second as m2, and so on. So we had worked out examples, okay, on how the this value, this function behaves. Okay. So for example, we said from where we start, it can decrease or increase and reach an equilibrium value. So we also said that equilibrium may not be uh, monotonic, but it can oscillate and then reach. That also we saw, it can either reach together or it can keep oscillating. So these are the things we saw for discrete time steps. Okay. Right. So then we started defining what is called most important concept, slope of a function. So note that this depending upon this function, okay, the behavior may change. This is what we saw. Maybe, yeah, we saw this here, that it is possible that it can oscillate, okay, in this case, and that, or it will, this is an equilibrium point, okay, at that point, you can either increase and come here or decrease and come here. All these things we saw, okay. If you have more doubts, you can go back to this video and see it. So now we are in the position of what is called as a slope. So we said that slope, we looked at this curve and said that you have to be very careful on this kind of curves. Typical in many disease progression, tumor progression, all those things, the graph will be something like this, we said. So for example, if you look at this graph here, they are slowly increasing. What do I mean by that? In 10 days, the increase is only this much, a small increase. That's all. So if I now, that's all is the increase. In 10 days, that's all is the increase. But now, when I go from 80 to 90, you will see that is the increase. So for the same time of 10 days, this 10 days, one increased by a very small negligible quantity here. On the other hand, okay, the same for 10 days, it increased a lot here. So now this is what we are now going to define as slope. So slope is the rate of increase in this case, rate of increase. Rate means divided by the x-axis. So in other words, we say that if I now have a graph like that, I think I'll take a fresh thing. Did I do that somewhere here? Okay. I'll do it again a bit so that. So what we said is that this is x-axis, this is y-axis. X can be t, y can be something else. We don't bother. So now let us say that this is 30, we are going to 40. So this is the increase between 30 and 40. Okay, this is y at 30 and y is equal to 40. Okay, and so we call this as delta y and this as delta x. So when I move from 30 to 40, which means that I add 10, delta x is 10, then I move in y from this point to this point. So delta y is this much. Clear? Now, if I had moved only 30 to 32, then this much is the increase in delta y. So you can see that how this line slopes. That's why it's called slope. Slopes is different. This is how it slopes. Slopes less. Okay. Slopes. When the line is like this, it doesn't slope at all. There's no slope. So this is the slope. This is higher slope and so on. So now the slope from the same point 30. If I go up to 32, then my slope is small. If I go up to 40, my slope is large. So I'm not happy with it. So I have to define what is slope at a point, say x, whatever be the point, is equal to limit delta x tends to 0. That means that take very, very small delta x. That's what in English that means. Delta y by delta x. Delta y by delta x. So note this carefully, that delta y by delta x is this angle theta, and actually tan theta is equal to delta y by delta x. So slope is nothing but tan of that angle that is formed, okay, when I join the two lines, 2 points, this point and this point, with respect to horizontal. So tan theta is equal to delta y by delta x. I mean, that's just a definition. They're not very, again, it gives you a physical picture. Apart from that, let's move on. So limit as delta x tends to 0, delta y by delta x is written as dy by dx. So this is the differential of y. I am differentiating y. Differentiating y simply means that I'm finding out the slope. That's all it means. No, nothing more. Right? So what does it mean? So if I have a function that is ft, okay, or fx, I'll take the same thing, it, fx. What it means is, so I'm going from this point to a close point here. So which means that, and I'm going to find the difference between the two as delta x, and then what is its corresponding variation in y. So I'm going to go here, I'm going to go here, and then what is that? So that is delta y. Okay, so this is delta x. So that means that I'm going to take fx plus delta x minus f of x. Okay, so this is x plus delta x, and this is x. So f of x plus delta x minus f of x is nothing but delta y. This is x plus delta x. So this becomes fx, and the corresponding point here, this becomes f of x plus delta x. The difference between them is equal to y. But I have y by delta x, so this is by delta x. And then I'll say limit as delta x tends to 0, and that is also called as dy by dx. Clear? Any questions? Right? Okay. Now, we also said that this rate of change of v, rate of increase or decrease or whatever it is, rate of change of rate means we are going to divide. That's all. Okay. So we talked about what is called as a differential equation. We are going to come to that with an initial condition. We're going to talk a lot about all these things. We give an example about those kind of slopes and limits. So we also said that the function need not be continuous. This is a continuous function. Just English keeps on continuously varying. This is discontinuous. At one point of time, there is a discontinuity. We gave an example of surgery for cancer where there's completely, there's a discontinuity of the size because of surgery. This is point of surgery. Okay, so we wrote a number of functions. These functions, we plotted it using MATLAB. Okay, and then we did all these things. Just now I taught all that. Okay, and dy by dx we had written. And we also recognized that there is a maximum. It's possible that these functions have a one maximum value or more than one maximum value or a minimum value and so on. So the functions which are like this are the convex functions and concave functions. Okay, so we saw that what is the minimum value. So if you remember, we also saw how to differentiate. I think the set of formulas which I had given. Okay, and now we also said that this derivative, again term, the same as differentiation, derivative, is helpful for me to find out, or the slope is helpful for me to find out what is the minimum value as well as the maximum value. So we had developed, so we also wrote that, also wrote that it can be written with one, symbol there as function. And when there are two functions, then this is the formula product rule, which we said. This is the product rule. Now, we also talked about the maximum and the minimum. So for example, look at this function. This is the slope, which is what is also called tangent, because tan theta is what it is. So tangent. The slope now keeps decreasing. It's very steep here, very steep here. And when it goes to 0, the slope is like this. The slope is flat. Then the slope again keeps increasing as I go down that side. Right? Now, I think we did the other way. Anyway, it doesn't matter. I mean, we took this as a function and then plotted it, doesn't matter. So now, if I now plot the slope for this curve, okay, yeah, this black, this will correspond to this. So it starts, because it is decreasing, it is negative, starts from the high negative value here, and then keeps going up because it is going to become less and less negative, and hits a zero at this place, zero at this place, and then keeps increasing. If the curve happens to be like this, sorry, so anyway, the red and red, black and black, if it is red, okay, it had a high positive value, just kept coming down, and at this place it hit the zero, and then goes on, okay, here, goes on like that to a negative value. So a positive value to a negative value has to cross through zero. So at that zero, it has the maximum value. So whether it's a maximum or a minimum, the slope is equal to zero. So this is well known. So these. So now, how do I find out whether it's a maximum or a minimum? I have got a function. When I put the function to be, I differentiate the function, then put the function to be zero, right? Then I find out the x value at which this derivative is a zero, that's fine. But how do I know whether it is positive or negative? Maximum or a minimum? So that's a problem. So now I take the derivative of a derivative. So this line, for example, this black line is going like this. I take the derivative of a derivative. So I find out the slope. Is the slope of the derivative, which is called as d squared y by dx squared. First, we started with dy by dx. So d squared y by dx squared. If it is positive, because you see, look at this, it keeps on increasing, crosses zero, goes further. So it is positive. So when it is positive, we get the minimum. So the condition is dy by dx is equal to 0 and d squared y by dx squared, the second slope is positive at that point here. Then we say that we have hit a minimum. Other way, look at this, it's coming down. So it has a negative slope. The slope is negative, it's decreasing. Why is it negative? This value minus, okay, this value, when we plot it, okay, it becomes negative. So it is decreasing, okay, decreasing plot. So the decreasing is where this function, I mean, this value is less than this value, it's decreasing. So in that case, okay, dy by dx is equal to 0 and d squared y by dx squared is equal to negative, then I get a maximum value. I get a maximum value. Clear? So depending upon whether it is a decreasing function or an increasing function, that is dy by dx, we get a maximum or a minimum value. Okay? Any questions?
The The slope at when the maximum or minimum is when the slope is 0, right?
Yes.
So at that point, that would be a horizontal line, right?
No. This happens to be a straight line. It need not.
But to be slope to be 0, it has to be horizontal line.
Which I don't understand.
So like,
see, the slope of this black line is this line. Okay, let me just remove it and replot it. Okay, now let's look at this red line, this red, okay, at the top, this red.
Yes.
Right? Yes. Okay. Now, what's happening to that red? It is negative slope, and then, I mean, this increasing reaches and then starts decreasing.
Yes.
Okay. So how will I plot it? This is positive. It's increasing, slowly increasing, and then. So how will I plot that? It will come like this, right? Yeah. So at one point, that is at this point, it reaches a 0 value. Yes. Right? Let's say this is 1, so it reaches a 0 value. So how will the other guy be? This black line?
Opposite direction. Yeah.
Opposite direction.
Yeah.
Okay, it is opposite direction. So again, yes, it will be 0 at this point.
Yes.
Okay, so this is increasing. That is why it keeps increasing. Between this, yes, and this value, why is increasing? So it's an increasing one. Okay, so yes, which means that we have minimum at that point. This is a decreasing one. So we get maximum at that point. When it's maximum, it is decreasing. Okay.
Yes.
Like this. So negative.
Yes.
Clear?
Yes.
Okay. So I can have, say for this example we gave, okay, and we can have d squared y by dx squared. We can have d cubed y by dx cubed, d power 4 y by dx power 4, and so on. We can keep, keep increasing the derivative. Slope of a slope, slope of a slope of a slope, slope of a slope of a slope. We can keep on doing that. Okay. But sometimes it may go on or it may become 0. We saw some formulas also, and we also said 2 functions, how to do that. And then we also said that if I want to calculate, for example, 2 functions, rho of t and v of t, we said that t is the independent variable here. So dm by dt is equal to rho of t into dv by dt plus v of t into d rho by dt. This is the formula which we gave. Okay, so the mass can vary because of volume or because of density. That's what it means. Density being a constant, when the volume being a constant, density varies, or density being a constant, volume varies. Both of them will have an effect on the variation of m. That's what it means. So I can have 2 functions. Note this carefully. There are 2 different functions. Both the functions are a function of t. And that's what happens. Clear? So we saw examples of it, how v varies, how rho varies. So we saw how dm by dt varies. Clear? So we said that an equation of this is a straight line. The equation of a straight line is y is equal to mx plus c. So now, when x is equal to 0, which is x is equal to 0 at this point, when I substitute it here, y is equal to c. When I substitute it here, x is equal to 0, so this goes off, so y is equal to c. So y is equal to c at x is equal to 0 simply means that that is the value of c. Then dy by dx, we saw that m into x. What is the dy by dx for this? M into x is
M.
m. Constant is 0. So dy by dx is actually m, which means slope of this line. Slope is a constant m. So wherever you go, it only increases by the same amount. So slope is a constant. It's a value of m. Okay, I'll stop here for a minute. Is there anything, any doubts, anything you have to clarify?
I just wanted to go to that parabola curve where you said there also the slope is kind of that first one, black and red.
Yeah, this one. Yeah.
Yeah. Here also the slope is kind of constant, no? I just wanted to know that. Ah.
No. See, this is actually the slope, dy by dx.
Okay.
Okay, this is the dy by dx. Right? Slope, dy by dx, slope is a constant.
Okay.
Slope is not a
Okay.
constant. Slope is a
of
constant.
slope.
Right?
Idod slope. Okay.
Idod slope. That is, you are absolutely right. I'm very happy you said that. Idod slope is the same.
Okay.
Right?
Right. Got it.
Slope of the slope. Fantastic. Very good. Very nice. Very good question. Okay. So then we did a few examples. We plotted it. Okay. Now, one way of looking at it is, given a function, we're going to see this quite often before we go to that level. Y is equal to function of x. And then we were finding out dy by dx. But it may so happen that you are given dy by dx, then find out what is the function which is resulting in this dy by dx. Very common. So such things are called differential equations. So we then found that very simple things like acceleration is change of velocity. Velocity is change of distance. So velocity is the first derivative dx by dt. Acceleration is the second derivative, which is d squared x by dt squared, and so on. So the famous Newton's law is F is equal to m into a, acceleration. This is the famous Newton's second law. So which means that F is equal to m d squared x by dt squared. Okay. So from which I can get x. So given this, if I get this, that is the differential. This is the differential equation. So this is a differential equation. So that's the next thing. So from here to here, it's differential equation. Okay, that is, sorry, from here to here. That is from here, I go back. So this is differentiation f to df by dx. Many things are like this. So the rate of cancer growth is a function of, that is volume, is a function of volume itself. So this is a differential equation. Then we saw a number of derivatives. What are the formulas for these derivatives? I said just keep it with you. Doesn't matter because you can always get it from ChatGPT or from MATLAB. Lastly, we define what are called implicit equations, which is, say, for example, I haven't. So when what is explicit? Y is equal to 2x plus 3. It's an explicit equation. Y is explicitly written in terms of x. So y is equal to x squared. y is equal to x cubed, and so on. Y is equal to sine x. Fine. Now, I can explicitly bring y to the one side very easily and write it. Whereas I have an equation of this form, then these are implicit equations. They are called as implicit equations. For if I get you're going to see this kind of equations a lot. As I told you, I'm going to take pharmacology as the base for defining all the mathematical equations. It becomes easy for you to understand and a good platform for me to also explain. Okay, so we will take a few examples from cardiology and so on, but pharmacology is very nice. You'll be able to appreciate all the things. Okay, but I need to go a bit more before we go to that step. So this is an implicit equation. So now you are going to ask me, what is dy by dx? Okay, so given this equation, what is dy by dx? So how I do this is I now differentiate each term here. So d by dx of x power 4 and d by dx of y power 4. What is d by dx of y power 4? Because x is an independent thing, I can understand. Now y is not independent, dependent variable. That's why we had asked for dy by dx. In which case, I write this as d of dy into y power 4 into dy by dx. So this is what we called as chain rule. Remember, this is what we called as chain rule. So what is that chain rule? So if I have a function y is a function of x, and x is a function of t. Obviously, y is a function of x is a function of t. So I want to know dy by dt. Now I don't have straight away, I don't have a relationship. Then I have to write it as dy by dx, which I get from first, into dx by dt, which I get from second. It is not, you're not supposed to do this, but just to understand, you can see that I get dy by dt. So similarly, I have y power 4, okay, and I'm going to write this as d by dy. So I want to find out d by dx of y power 4. How do I do that? I know y is a function of x. So I'm going to write it as d by dy, the first term of y power 4 multiplied by dy by dx. Because y is a function of x is what I have written as, and I want dy by dx. That's all. So that is why I get an equation of this form, from which I can differentiate each one of them. This I am differentiated as if y is equal to x, 4y cubed, as if it is x power 4, 4x cubed, and so on. Here, any questions? Any questions? So this is chain rule. As a chain, I'm applying that rule. This is called as a chain rule. Many examples like this. Okay. So we saw this a few example, and then how we said dv by dt. So v is a function of r, radius of, say, for example, a spherical tumor. But r varies with time. The question is, how does v vary? What is dv by dt? So it's a function of r, function of t. So we said we will differentiate this function with respect to r and then write it as multiplied by dr by dt. So when I do that, I get dv by dt to be a function of dr by dt. So this equation becomes important because ultimately you want to know how the volume changes as the radius change. So what do you look at? Look at this. So When R is high, a small change in radius would give you a large change in volume. A large change. So number of, say, cancer cells will increase proportional to R squared. So even small change as R keeps increasing, dV by dt keeps increasing more to power. So we had this kind of explanation for example, for the few more examples we saw. I'll come to that. We saw that also in the case of fluid flow or blood flow as well. So the way radius decreases, okay, then the resistance increases 1 by r power 5. R power minus 5 means 1 by r power 5. So the resistance keep increasing very much when the blood vessel narrowing takes place. So this is all also we saw. Then we said that when there are two functions, how to write it? We had just written it as the product rule previously. The same thing we wrote. Okay, sort of we are there. We have completed a quick review of all the things, right? So any questions? Any questions? I would like you to revise once. I'll send you this as a PDF file. I would like you to revise once, and then if there are any questions, please ask me. Okay. Now we come to another important concept in calculus, which is called as integration. So suppose Dr. Sundar wants to find out, okay, the PV loops area. Area has become extremely important. The work done, okay, and so on. We'll see that later in the course. But I want to find out areas. There are so many examples where area becomes important. How do I first thing is, how do I find out area? But finding out area has been always a problem or an interesting problem in history. Okay. So areas have been in Indian mathematics, what they call as Vedic mathematics. So mathematics come from time immemorial. Area was a very important thing. In Greek mathematics, area became very important. Archimedes is one of the guys who actually looked at areas. Okay. Later on, area became a core in calculus and was supposed to have been initiated by Leibniz. Okay. And there are so many big names involved with this: Cauchy, Riemann, and so on. Area has been a very important thing even in Indian mathematics, where the Kerala school of mathematics was one of the earliest. In fact, it's been debatable whether calculus originated in Kerala or in UK. So that's a very interesting debate. Who did this first? And integration and differentiation were supposed to have been a part of Kerala School of Mathematics. Anyway, so there are very a lot of people who do research on it. Very interesting thing. So the first thing is that suppose I want to find out the area, this area. So what do? You may put one grid here and then count the grid's area. This is rectangle, this is rectangle. So you can just count the area and then say the total area is this much. Okay, so this is easy way of doing it. But as you make the grid finer and finer, you will get better and better approximation. But we are not here in the business of drawing grids. So let's look at a curve like this, right? And I want to find out the area under that curve, this blue one. So how do I find out the area under this curve? What I can do is, I can take some rectangles like this, okay? And then find out the area under these rectangles and then add. Here, I can keep on approximating that curve by means of a number of rectangles and then add them. Now, when I make the rectangle finer and finer, okay, then obviously I will approach this curve closer and closer. So now this area, if I now just add, so up to this, say for example, so I will get this, that's the area I will get. So what is that I have done? I have left out that area, that area. That is the error in just adding this rectangle. In this case, that is the error which I get. As I make this area smaller and smaller, in other words, subdivision smaller and smaller, or in other words, this delta x smaller and smaller. Don't you see that as I make it go to 0, don't you see that the area is very well captured? Right? So go back, and when we go back to when we revised it, we saw that sigma. So suppose each area is, so this area is A2, this is A1, A2, A3, and so on. I can write AI, sum of AI. Okay, I is equal to 1 to say n. This is the n. So what does this mean? Can someone just remember what this is?
A1 plus A2 plus A3 plus
Etc.
AN.
Up to n. Right? So I can say that as n keeps increasing, what does that mean? The width keeps decreasing, and I have got more numbers. Okay? More numbers. Number of rectangles. What happens when I have more number of rectangles? My area now becomes closer and closer to the actual area. Isn't it?
Yes, sir.
Now, I'm going to remove all this and write it. I'm going to remove all these things and actually write the area of 1 point. So let us say that this is this point. You say x, this is, say this is 1, 2, 3, x4. Okay. Now I want to write down a formula for this. Can someone tell me what is the formula? This is x5. Let's say that's x5. Can someone tell the formula for that rectangle?
X5 minus X4 into.
Correct. So let me call that as delta x.
Delta X.
Into
Height of.
what is the height? That is this height, right? Sorry, this
Delta
height.
Y.
No, what is that? What is this point? So this point I have to know. What is that point?
The slope.
No, that point.
F of X of 4.
Yes, that is function that y function of x4, right?
Yes.
So the function of x4 is this point, because what is the function y is equal to function of x is this curve. So when
Yes.
x becomes x4, y is this y4, right?
Yes.
So similarly, x of 5 into this delta x, x6. So delta x is x5 minus x6. So this because the rectangles are of the same width, I can use the same delta x into delta x, and so on. Clear?
Yes. Yes.
Okay. So I can now write down that the sum of this whole thing, using the same symbol as in that book which I gave you, the sum of the function of, instead of this x5, I mean x5, x6, I'm using this ck, okay, and making a small difference in that, in the sense that I'm going to have, look at this, look at what's the difference. Okay, before I go, I think this is, so I'm not, so what I'm going to do is I'm going to do a small variation with this. What is the variation? Oh, can you find out what is the variation between this and this? Okay, this is function adding. So what is the variation between this and this? The way a rectangle is drawn, right? Here,
Rectangle
all
is,
the
yeah,
rectangles that are drawn are below,
below the curve.
okay,
Yeah.
right? But here, I'm going to draw rectangles like this. Okay, clear? So which means that this is addition, okay, that is plus error, clear? And this is minus error. Here, all of them are minus errors. Less errors, less, so minus error. So here, there is one plus error and one minus error. So when I draw like that, it is possible that I will I will gain here, I will lose here. Okay, they may compensate each other, my error will be less. Clear? But this, so I have a I take the midpoint. Don't worry about it, it's very simple. And just say that function of the midpoint, which is called ck, multiplied by delta xk. So sigma k is equal to 1 to here. That's all. So I just look at the difference. There's a difference in the way the rectangles are drawn. This is called as the sum. Okay, and there are various names to it. It's called Riemann sum, but you don't bother. Is that clear? Okay. Any questions? I just want you to spend a minute looking at these two graphs and then pick
I
up
didn't understand the last graph, sir.
this graph.
The second, the large one, where it's going positive. When you looked at the other, the top one, that small rectangles, that's going straight. No, there's no negativity, negative
No,
thing
no,
there.
no, 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 no. Let's
Ah,
understand this. Let's understand this carefully. Now, so what is that I'm doing? This line, I want to find out the area here. Okay. In order to
Yeah.
find the area, I draw a rectangle. This is very straightforward to just illustrate. So I draw a number of rectangles. Okay. And then I know the area of the rectangle. I will find out the area of the rectangle. That's what I did here. Right?
Yeah.
So when I add it, I'm losing this area. I'm losing
Correct.
this area. I'm losing this area. So that is the error.
Yes.
Okay. Now, what I'm going to do is, instead of this rectangle, let me draw it here. I'm going to take rectangles like this.
Can't see, sir.
You're able to see here?
Yeah, yeah. Ah, yes, sir.
Okay. So I'm going to take rectangle. So previously, I had taken rectangles like this. Okay. Now, I'm going to take rectangles like this.
Right. Right, sir.
Okay. So I gained here, it is plus.
And
And
then
I lost
got
here.
it, sir.
So,
Yes.
so that is what it happens here. So I'm gaining here and I am losing here. That's better than drawing rectangles like this. Okay. So now this is the function. This is the center of this rectangle, which I called as CK. And this point is function of CK. So function of CK into delta X is that area.
Okay.
Clear?
Yes, sir.
Very easy to slightly complex. Now, when I keep on reducing delta X, then I will be able to get the curve area brilliantly, no problem. Delta X tends to 0, I will get exactly the curve area.
Correct.
Okay. So, which means that is a sum, I said, function of.
Sir, the
Yeah.
height of the rectangle is same for CK and xk minus 1, right?
No, you look at this. So this is the height, right? So
Yeah.
at X, I'm calculating here.
Yes.
Right?
Yeah.
In this case, I'm calculating, the rectangle is like this. I'm calculating at the center between the two.
Yeah.
Look at this. So I'm calculating at the center. The previous case, I was calculating at this point and then drawing the rectangle like this.
Yeah.
Now
Okay.
I'm drawing the rectangle like this, and so I'm calculating the height at the center.
Yeah. Now got it. Yeah. Yeah. Understood.
Okay.
Yes,
So this is the sum. And this is what is called as an integral of this function x dx. The sum, as delta x becomes 0, gets converted into that symbol, which is called as an integration symbol. Summation becomes integration. So summation and integration are the same. Okay. Now, what is this connection to differentiation? We'll come to that later. First, let us understand this. So summation and integration are the same. This is called as the integral sign. Now, I had one more k is equal to 1 to n. Okay, I had that. Now, here, I am going from, say, A to B or 0. Say, let me say, I'm going from 0 to that value of, say, B. Instead of this two things is replaced here. From where to where I'm going, from 0 to B. So B. So these are called as limits of integration. I'm going to revise this again the next class. Limits of integration. 0 is called lower limit. And B is called upper limit. So this is called lower limit and the other one is called upper limit. So this is So if I want to now find out an area, if I can somehow get this integral evaluated, fantastic, I'll get a very good area. How do I evaluate it? We'll see that in the next class. Okay. So this has close relationship with our differentiation. So we will sort of complete the whole thing if I know this integration as well. After I finish integration, we'll have a class where we will do a lot more problems. I'm not doing it now. After that, we will do problems only with MATLAB, not independent of it. After this, we will. Okay. Is that clear? Any questions? No questions?
So I'm asking a very stupid question.
No question is
Now,
stupid.
no. You've told me so many concepts in integration, calculus, tan, sine, all that. Now, how much as a doctor will I be involved? I mean, when I'm doing a problem, how should I know what I should put where? Or
So
I
you have
do
to
not
wait for
know.
a couple of classes.
Okay. Okay, sir.
All these things, whatever I am teaching you, has applications in medicine. That day,
Okay.
in the last class we discussed, one of the things we discussed. For example, as I told you, now PV loop is very important. In fact, we are working on PV loop for cardiac failure patients. So we are looking at this area. Okay. Now, how do I find out this area? I have to use that integration. Okay.
Right.
So area of a curve becomes very important for so many reasons. So I'm going to take all these things together. Suppose you give a drug, how does it react? We're going to see this. How does a tumor grow? We're going to see this. All those things, examples, we will see it once we know. So because without knowing some fundamentals, I can't take an example. So with
Yes,
this,
sir. Yes, sir.
we will go to the examples afterwards. Clear? So
Yes, sir.
then you will know where you are using all this. You will know everywhere where all you're using. Then you'll start understanding, I feel, a lot more stuff than
Right.
what you've done so far. Okay. So, for example, we are talking about AI/ML all the time. If you don't know this, there is no AI/ML.
Right, sir.
Okay. Okay. So we'll stop here. If there are no more questions, please think about it. Maybe we'll see that your questions in the next class. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you.